Yep, so we had our particle in a box. We had our setup where this was the length of the box and it went from, went from what? Yep. We had 3 regions. Region 1, region 2, region 3, and we set up our bounds and whatnot. We determined what is the wave function in region 1? Yeah. Just because if we didn't, we'd have infinite energy, right? Same thing was true for here. Then, Lily, like you said, we determined psi, we normalized it. What was the normalized wave function for this range? Yep. Yep. So now this is our wave function. It's been normalized. So we have that. We're in a good spot. We have everything we need. Okay, so we picked sines because cosine at these edges would have been a value of 1, so we wanted to stay away from that. We could have picked some exponent and went with that, but it just ends up being almost the same mathematics. Okay. However, we wanted to apply the Schrodinger equation to this system. What's the generic Schrodinger equation? Yep, H hat. What have we yet to calculate? We've yet to calculate the energy. How about we utilize this and calculate the energy for this generic expression? The other important point, this n, we put a restriction on it. We said it was quantized. It could only take on discrete values. What are the n values we could have? Yep, could have 0. So on, whole number integers. I suggest we exclude 0 from this guy because that means we don't have a quantum particle. So the restriction we're going to have is n goes from 1, 2, 3, and so on. This n you've seen many other places. What is it? Yep. Okay, so we're going to apply this to that, but we also know several other quantum numbers that you learned in general chemistry you're probably using in inorganic chemistry. We're going to be on a journey to find the rest of those things by applying it to simplistic systems, and we're just going to keep on getting more complex until we get to molecules. Okay? Before we do that, though, let's take the simple stuff. Okay, H bar. The nice thing about region 2, what do we know about the potential? Yeah. So therefore, Hamiltonian operator, does it have any potential energy operator? Nope, just has kinetic. And we know what that kinetic energy operator is. What is it? Yep. 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 With respect to which variable? Yep. Okay, and then we have our wave function. And that's going to be equal to E psi eventually. Okay, at this point, it's just calculus, right? Let's apply the first derivative. We apply a derivative to that guy. What are we going to get out? Yeah, I'm going to move that over here. Yep. And then what's here? Yep. Cosine. Yep. Okay. Still have to do another derivative. Let's apply another derivative, negative h bar squared over 2m. Doesn't change anything. Take another derivative of this guy. Mm-hmm. Yep, over a squared. Yep. Yes. Okay. Ellen, there's nothing wrong with you wanting to put that out front, but I'm just trying to do this to keep it simplistic for us. Why did I keep this thing grouped over here? Yeah, this is our wave function at psi of x. What's this part? I'm going to circle in blue. Yep, that's our energy. Okay, so now we can get rid of the wave function on both sides. We don't have to worry about it. Our energy is negative h bar squared over 2m times negative n squared pi squared a squared. Can you simplify that a bit more for me? And, yep. All right, perfect. So this is the energy expression, and a lot of times you'll see a sub n there, where what things can you change in this? N, yep, depending on what energetic state. Here, what's the ground state? Yep, n is equal to 1. Therefore, the energy of the ground state would be h bar squared pi squared over 2a squared. What else could we change in here besides the n value? Yep, you can change the length of the box, and that has consequences for it. If this length gets bigger, what happens to the energy? Yeah, exactly. It gets smaller. Do you guys know what cyano dyes are? Okay. Have you ever dyed wool before, like in high school, or cloth? Maybe not. Cyano dyes were typically used to make colorful pigments to bind to wool and cloth, and that's how they used to dye things. We operate under similar aspects to it, but you can actually model the length of those cyano dyes with a particle in a box and get the color of whatever the dye is going to look like based upon messing with that chain length. So there's very few applications of particle in a box, but that is one of them. It's pretty neat. Okay, so if n's equal to 1, that's the ground state. What would be an excited state? Yeah, 2 or 3, where n is greater than 1. So that's going to change the value of this. When we're talking about transitions, what do we mean when we say a transition? A change in E, a delta E. So in some cases, when you're looking at excited states or a transition to an excited state, you need to be concerned with delta E, like on that daily problem, okay? Are there any questions about this one? Okay. The value of the energy, what do you notice? You plugged everything in, it's always going to be what? Yeah, will always be a positive value. That's a bit different than what you guys see in lab. What do you always get for your energy values in lab? Yeah, they're always negative, or they should be. If you have a positive, something's gone really, really bad. We're going to talk about why that is as we start applying this to more complicated models. Okay? No questions about that, right? You feel like you could do this pretty easily. Okay, good.